So I actually I added Jupyter as well to the mix here. It was always there, but I felt it was important to explicitly call it out. As I was working on the presentation, I realized that that's really what this is about. So for me, at least. So what I'm going to be talking about is high-performance computing for individuals, and for individuals who maybe don't have backgrounds in high-performance computing. So the talk is designed around achieving higher performance with using higher-level languages. So there's not going to be any NumPy, no CUDA, nothing fancy like that. There are other tools that provide these higher-level wrappers for higher performance, like Spark, and one that I'm really excited about more recently is Blaze, the Blaze ecosystem, which is built around the SciPy ecosystem. But what I'm going to present here today is built completely, mostly from the ground up using NumPy by myself. So let's get started. So I do most of my work in at least my personal work and my more computational work in Jupyter. For me, Jupyter it's a wholly different programming paradigm. It's not an IDE. I like to think of it, or in trying to come up with the words to describe it, it's a living runtime. So it doesn't replace Vim or Sublime or PyCharm or whatever you use. For me, it replaces if name equals main. So in what I'm going to be tackling here is this what I'm calling medium-sized data. So we're not talking about huge data problems. We're talking about data sets that are small enough that we can use traditional database tools like Postgres or Mongo or those sorts of tools. It's small enough to fit in memory, but it's big enough that it's unwieldy. It's hard to work with, especially with Jupyter, especially with kernel crashes and long processing times. The problem in particular that I'm solving here is a Kaggle problem. It's an open Kaggle data set. It's the Red Hat data set.
Medium size, do you mean like megabyte or?
So this data set is about, like combined, is about 175 megabytes. It's not huge. I think there's 2.5 million rows when you do the join on the tables, and we'll actually get into that. Earlier today, Ben Hamner spoke in here, and he talked about the people that were most successful at Kaggle problems. And these are not the people who are going and optimizing their system to run the latest algorithms and to run on these on GPUs and all these sorts of things. These are the people who are setting up systems in which they can iterate quickly. So toward that, this is a system in which we can combine the fast iteration of working in Jupyter, but also get some better performance. So this is just a sample of what the data set looks like. What was interesting to me about the Red Hat data set is that it had zero domain knowledge. It's literally like characteristic 9, type 2, type 4, type 1. There's no domain knowledge here. And actually, to speak about the size of the data set here, these are some different sizes on the CSVs that you're given. So you've got a test set that has 500,000 rows, a training set that has 2.2 million rows, and a people set that you do joins with on the training set, about 200,000 rows. So my training is as a scientific software engineer, at least my training in school. And while I was in school, this paper right here is probably about the most influential paper that I read while I was in school, especially around the software development process. So I'm going to read a quick paragraph from that paper. He says, "The design question that you will face most often as you formulate and execute a series of computational experiments is how much effort to put into software engineering. Depending upon your temperament, you may be tempted to execute a quick series of commands in order to test your hypothesis immediately, or you may be tempted to over-engineer your programs to carry out your experiment in a pleasingly automatic fashion." And when I post this will actually be there'll be a link to this paper right here, command lines versus scripts. So for me, Jupyter is the best of both of these worlds. I use it as an interactive environment in which my scripts become commands and my commands become programs that are executed from within Jupyter. So I've got a series of commands that I'm running right here. And ultimately what I'll do is I'll fine-tune these until they're ready. I'm just running them repeatedly over and over again. And I'll just pop them into a file in my library, and then ultimately just import that command and run it as a single command. Sort of refine my whole ecosystem. I don't want to call it I guess it's a program. I refine my program that I'm running from Jupyter in this way. So Jupyter has become my go-to, and this is a project written from the ground up around working in Jupyter. One other thing, just this picture right here, one other thing that I insisted to someone the other day, I said, look, Jupyter is a command line, and he didn't believe me. So I sent this to him, which works. Usually, you can actually run bash explicitly by putting %% bash and then putting some bash there, but apparently ls just works. So working with these medium-sized data set problems, it can become unwieldy in Jupyter. So my solution to that problem is infrastructure as code. So I do this completely in Docker. If you're not familiar with Docker, I'm going to talk briefly about Docker. So Docker is not a virtual machine. And here's a few links to post that. You can find those later, but I'm just going to say that right now. Docker is not a virtual machine. So in discussing it, I've sort of come up with two analogies for what Docker is. There's this weak analogy, the object-oriented programming analogy, that a Docker image is a class, and a container is an object or an instance of that class. And I think you can get somewhere explaining Docker with that analogy, but I do think it's weak. The stronger analogy is the compiled language analog. So in that case, an image is like a compiled binary, and a container is a process that running that compiled binary. So I mean, this is explicit. When you do a build on an image, you are building that binary, and then when you're running that image, it's like you're running the process. So here we go. This is what Docker looks like overall, and from now on, I'm going to refer to them as processes. So this is basically what I'm going to be running right now. We've got the host that can be for me, it's my Mac. It's local. It can be an Ubuntu machine running remotely in DigitalOcean, or it can even be a swarm, a cluster of machines that's been combined to behave like a single Docker machine. And this is sort of what we're going to be running. These are the processes we're going to be running. We've got several Python workers. We've got Jupyter. We've got Redis, Postgres, and a web interface to monitor the health of our different workers. I did have one thing that I wanted to show here. Can I put that up there? Yeah. And let's actually, I can't see this. Let me, how are we going to do this? Can you see that? That's the important thing. Yeah. How about that? OK, so I actually have a makefile here that I use to do all my interfacing and that sort of thing. I will show that to you in a moment, but for now, I'm just going to do this, make bash Jupyter. So I'm actually right now going to open a bash shell into my running Jupyter image. And you can see that I went from me on my machine called Bambata to Jovian, which is the Jupyter user, if you ever looked at the Docker file, and on this Docker container. So now we're inside the Docker container. And for what we would expect from the next command, this is my local Mac. And I'm going to run psaux here. And we've got hundreds of processes running on my Mac. So let's go back to, here we go, back to the Docker container. And we have 4. So we've got 4, and one of them is psaux that we just ran. One of them is the bash process we just ran to get into the container. And then we have these two right here. I am not going to be talking about Tiny at all, but I'm happy to talk about it in the hallway afterward. And then we have Jupyter running right here. So the idea with A Docker container is that each one runs a single process. Bless you. So, how do we define these processes? We define these processes using a Docker file. We have an infrastructure that we're building, and we're going to be using a docker compose.yaml file. And then we're going to be using these command line tools, Docker, Docker Machine, and Docker Compose, to interact with our system. All right, that's enough Docker. Everybody got it? I'm sorry? Right now, I'm running, when I show you Docker, I'm running it on an Ubuntu instance running on DigitalOcean. But we could just, I could fire up the same, I'll file it, I will fire it up locally as well. That's part of the point. So this is the system that we're going to be building. We've got Jupyter, we've got our worker monitor, Redis is our message queue, and we're also going to stuff values in there if we want to pass them back and forth between different processes. Our database is holding our data, and then we've got some workers. And we're interfacing, we're sort of controlling the whole system using a makefile. If you're not familiar with a makefile, it's super old school. It comes from, it's a Unix thing. It comes with just about every Unix system. Some of you might have heard of a rake file, which is a Ruby thing. And I think Python even has something called Fabric that does sort of the same job. It's designed to sit at the root of your repo and to run sort of your maintenance commands and any sort of commands that you're going to be running repeatedly from the command line. You can put them into your makefile and sort of forget about the complicated syntax of these commands that you're running. So this is our system. We're defining the system using docker compose.yaml. We're managing the system using a makefile. We're going to be executing code using Jupyter. And we're going to develop editing code in place. So this is the repo right here. We've got our assets, static files. We've got binaries, which mostly the binaries that I have in there, I only have one or two, and mostly they're for interfacing with the swarm. We've got our raw data, documentation. This is where we're going to be, Docker is where we're going to be containing all of our Docker files and the requirements that go with those containers. So the Python containers are going to need like a requirements.txt file. The Postgres container is going to have its data sitting right there. And I keep saying container. These are, the Docker files are sitting there. We'll get to it. Sorry. Our notebooks, our lib contains all of our source code. There's the makefile that we're using to run everything, and a README, and then the Docker Compose. So first, we're going to talk briefly about the Docker Compose file. So again, these are the 5 kinds of containers that we're going to be running: Jupyter, Postgres, Redis, RQ, which is our worker, and the web server, which is going to be monitoring our workers. So this is our docker compose.yaml. So the first statement is a build statement. You're either going to use build or image in that location. If it's build, it's going to be looking for a Docker file. And then when you build it, it's going to pull that Docker file and build it. So that's referencing a Docker file within this folder. And maybe I should show that to you. Let's see, I'm still inside my Jupyter container. So let's do. So these are the 3 container types that I'm actually going to be actively building. I've got a Jupyter container type, so I've got just the Docker file and a requirements.txt. I've got a Postgres container file, which has actually my CSV files and then actually some SQL commands. And then I've got my Python container type, which has a Docker file and, again, requirements.txt.
I have a question.
Yes.
More about Docker. Are you choosing just to have one process per container?
That is actually a best practice recommended by Docker.
Stack on one container.
That is right. That is right. One process per container is the Docker recommended best practice. So this is actually where we're pulling that Docker file from. And we've got a few more options. And then, I'm sorry, this is the Docker file that we're going to be running. So we're pulling an image from Docker Hub. We're pulling the Jupyter SciPy notebook image. This switching users is actually something that I know from working with the Jupyter images, that you want to be installing things as root, but then running as Jovian, which is the name that Jupyter chose when they defined their images. So these are the different requirements that I specifically need that didn't come with that image. And they're mostly built around, I wanted to get Blaze running on there. And there's a few other, I think, interfacing with Postgres doesn't come out of the box. Interfacing with Redis doesn't come out of the box, that sort of thing. We're linking to 2 other containers. So we're going to actually have, as an environment variable, defined links to those containers, to our Redis container and to our Postgres container. This is actually critical for if you're going to be running Jupyter from a Docker container. You have to mount your local volume to this location. And when you do that, you will have access to your local files in that Jupyter ecosystem when you go look at it in the browser. And ultimately, I'm going to be exposing port 888, where Jupyter is running inside the container. I'm going to be exposing that on port 8003 on the host system. This is a lot. So if you have, just shoot out questions if you have them. Yes?
So on that last trick you just said, so Docker internally has its own port structure?
That is
or
correct.
Are those ports within the main machine?
So this port right here is the host, and this port right here is within the container. That's correct. It has its own port system.
But they're all virtual. What does that really mean?
I don't know.
Okay. All right.
This is how you make it work. Yes?
So for the persistent volume, I noticed that your directories in the Jovian user, right? So how do you mount volume on your?
That's good. Let's talk about persistent volumes. Yes. So this directory right here is inside the Docker container. And it's defined actually within, if I take a step back, it's defined within Jupyter's SciPy notebook Docker file. And you can go find that on Docker Hub, or they have a GitHub with all their Docker files. They've actually defined the working directory. It's called workdir. They've defined that for this container to be home/jovian/work. Now, I could put this Docker file into any local directory that I'm working, and then I'm just pointing period, which is the directory I'm in right now, to that location, which is going to make this directory available in that location inside the Docker container. But it's also going to create a link, a backlink. So any changes that I make running inside Docker are going to be updated here. And there's actually a pretty decent, I'm just going to show this to you real quick, because this is really nice. If you're just running Jupyter, let me get it over here. Let me get bigger. If you're just running Jupyter, so for example, if you're going to do Docker run Jupyter/SciPy, I'm not going to run it, but thank you. I went back and changed it to the same thing. So what you would do here to mount it is -v, and you know it wants to be in /home/jovian/work. There we go. Now this is the trick. So what this is going to do, you put it in backticks, that's actually going to execute bash inline, and that's PWD, that's print working directory. So this is actually going to mount the current directory to that location. So if you just want to go and run a Docker image of Jupyter without doing all the Docker compose, this is a great way to do it. -p 8888, too many. There you go. This is how I run Docker. Just if I just want to run a single image with no, all right. There we go. That's how I run Docker. Let's see. So that's mounting a persistent volume. And again, the one on the left is the host. The one on the right is, this is confusing. This means I'm going to access this on host colon 8003. And I'll show you that in just a moment. So the next image we're going to define is our Postgres image. I'm mounting to /home this time. And I'm going to mount from this volume Postgres data, which is actually defined right here. Now, the reason that I'm doing this is that so I can shut down my Docker system over and over again. And my data is not going to be saved to this image. It's actually going to be saved to this image. And it's not actually running anything. The only thing this image is doing is running this command. It's echoing data container for Postgres DB. And this is actually, it's not quite, it's persistent in a different sense than the previous persistent sense. This is in order to not lose my database data every time I bring the system up and down. So the data is actually being written to a Docker container that's not running. Let me show it to you. So I'm running Docker PS. Now I can't run, if I run Docker PS, we're actually not going to see that image. Here's my 5 images. You just see Postgres. You don't see the data image because it's not running. So if I run Docker PS-A, show me everything, even the containers that aren't running, it is going to show up there. And it's not showing up there. Here it is right here. And it exited about an hour ago. It's not, that's when I brought this system online. Any questions about that? I can talk about later about that. It's kind of a tricky thing. This is the actual Docker file for that Postgres image. Now this right here, this is really cool. It's part of the way that Postgres has defined their Docker images. Now most major, Postgres, Python, Ruby, like all the major folks have their own Docker images, and they do their own tricks with them. And one of the things that Postgres has done is any SQL files that you put into that directory will get run when the image boots. So I've actually written my SQL instructions into that file, and when it boots up the image, it's going to copy these CSVs to the table using that SQL. Now what's cool about this is I can instantiate the database just by bringing the system online. And I can shut it down and reinstantiate the database just by running a Docker Compose build. And again, that's a mechanism for persistent data. Now this one is slightly different because I'm not doing anything fancy with Redis. I'm just pulling the Redis image from Docker Hub. So it's just going to go to Docker Hub. If you don't put anything, it's going to pull Redis :latest. So it's just going to pull Redis when I run it. Again, we're doing the persistent data thing. Now we are doing a Docker file for our RQ image. And I also want to call out this command that we're running. This is going to get run when the image starts. It's going to run RQ worker and then pull these config settings from our library of code. This is the Docker file for that container. Mostly it's just installing from requirements.txt. You do see, I mentioned workdir earlier. You can see that this is how you define a work directory. I'm defining workdir right there. Again, it gets the links to the other containers. It starts that process on run, and then it's mounting the local volume. What this is going to do is actually make my library of code available to the RQ image. And actually, it's going to make it available in real time. So as I'm actually developing code, if I kick off a new worker process, it's going to pull the latest code. And then this is the web server. More of the same. We've seen most of this, except this one's going to be available on 8002, and then that's the process that we're going to run. So next, I'd like to talk a little bit about managing the system. Now, I've actually, as you've seen me do this already, I've actually run a bash process to get into the containers already. I've also written mechanisms to go in, get a Postgres CLI just by running make Postgres, and get a Redis CLI by make Redis. And then this is actually how we run the Docker Compose mechanism. So if I want to build all of the containers, which is necessary just to run the system, the process of running the system is you build it and you run it. Very similar to writing a program in C. You compile it, and then you execute it. So to run it at all, I have to build it first, and then I bring it up, or I can take it down. And I can also, RM is used to remove old containers. So this is what I would do if I actually wanted to nuke the database and wipe it out completely. I would do Docker Compose RM. Just bringing it down is not going to erase the database because we're writing the database to those images that are already shut down. And this is actually, and we also have a make swarm command that I can run. And I also built a few for writing the presentation using Pandoc and generating a report. So this is the actual system. Let's bring it up. We might need to get a web browser over there. So this is my web interface to monitor my worker health. And here is Jupyter. And I've already gone, let's actually go up to the top level just so you can see what it looks like. So literally what it does when I mount that persistent volume is it mounts the repo in Jupyter. And I can actually go in, I actually go in here a lot of the time and just look at files through this interface, especially if I'm working on a remote server. Or I've been known to go into a terminal and launch Vim from within Jupyter, but we won't do that right now. Let's go into our notebooks, and let's take a look at our working environment first. And it just started up. Let's run that again. So you can see this is actually how I run bash explicitly, %% bash. And then I'm running env to see all of my environment variables that are available to, now keep in mind, this is within the Jupyter container. So these are all the environment variables available to the Jupyter system. And let's see what we have in terms of Postgres. So we've got the location, we've got the protocol for Postgres, we've got the IP address for Postgres, we've got the port that it's running on. And these variables are actually how we're going to access our Postgres system from within Jupyter. Absolutely, and the repo is on GitHub as well. Yeah. There's a link on the first page. I'll put it back up when I'm all finished. Yeah, this is all, the repo's there. If you want to go check it out right now, it's joshuacook/Red Hat. If you can go look there right now. Yeah, definitely. I guess, and one thing that I actually meant to do, and I didn't, is bring it up. So this is actually it running. Let's bring it down. I just did a hard kill. That's probably not a best practice, but. So this is how you bring it up, make up. It starts running. And it's tailing the logs for all the different kinds of containers we have. So we've got Jupyter, web server, RQ. If we go up, we would see Postgres and Redis, but we're not going to see much from them after they get going. So let's look at how we're going to do some distributed processing with this system. It's because I shut it down, remember? Let's close this one, actually. And let's go to test queue. So what's going on here, can everybody see this? No? Yes? Okay. So right now, this Jupyter notebook is running inside the directory IPYMB. So the first thing I want to do is actually go up a level. Because if I do that, now I can access the library of code as just regular Python modules. So I'm going to, from lib.app, import Q. And let me show you what's happening there. Oh, right, it's in the init file. So this is lib.app, and you can see Q is defined right here. It's a queue with a connection to Redis. Redis being defined right here. Looks like I have some legacy Mongo code there, too, from an earlier iteration. So I'm basically pulling in a connection to add jobs to our workers via the Redis queue. So the next thing I'm going to do is import test function, which is a really complicated function that does this. So this is test function. And let's add it to our queue. And you can see it's done. I got control back from Jupyter. If we come over here, the jobs are going. They're ticking off. Because that one's going really fast. I queued 1,000 jobs, but it's just passing them straight through. So I mentioned, that I built this in order to work on a Kaggle competition. So the next thing I really would want to do for this is look at the actual data. So one method that I wrote to do that is connect to Postgres. I got tired of typing this over and over again. It's pretty ugly. And you can see I'm actually using one of those environment variables. I'm pulling in Red Hat Postgres, port 5432 over TCP. And then I'm going to return a connection and a cursor, which is just standard psycho-PG. That's how you use that library. It's the standard Python library to interface with Postgres. So let's open that guy up. So I'm using the same technique. I'm going up a directory. I'm importing. This is where I'm doing that. I'm importing that method, connect to Postgres. Now, in terms of the development process, the first 50 notebooks I worked in, I literally had that code in here. And I would just copy it and paste it and copy it and paste it. And that's how I would connect to Postgres. So I finally just, I got tired of typing that. And I abstracted it into this library. And now I just pull it using that method. So there goes that. And now I'm actually going to be connecting to the Postgres database. And I just counted the number of rows in the people table, number of rows in the action table where the outcome is null. That's the test set. Number of rows in the action table where the outcome is not null, the training set. So this is where I'm actually getting into, I want to count like unique types and that sort of thing. So I'm looking for the number where the data type is text, the number where the data type is Boolean. Basically, I'm just running SQL here in my Jupyter notebooks, which is getting harder and harder to see. And I'm just running that sort of thing to go through and look at all of the different data types. I'm actually running some averages here to look at the average of, I believe those are they're Boolean types, so those are just, I guess those are closer to being false on average than being true. And because I've abstracted this method out and I just have my cursor here, I don't have to be running that connect to Postgres every time. So what I ultimately decided to do for this data set, because as I showed you, it's mostly categorical data, and it's categorical data that has no meaning whatsoever. It's just characteristic 1, characteristic 2, and so on. What I ultimately decided to do was to one-hot encode the data. So let's look at how I did that one-hot encoding. It's this one. Okay. Same thing, connecting to the database. You know what? I didn't want this one. I'm sorry. I wanted this one. So this is actually where I was because I did write this I didn't use sklearn, I just used pure NumPy. As a thought experiment, I'm actually trying to learn these things better. So I probably would get better performance using libraries, but I wanted to do it for myself at least once. So what I'm doing here is actually writing a method to actively select 2 columns and then one-hot encode those columns just so I can sort of look at it and get a sense of how it's done. So right here, I've actually defined the 2 columns that I want to get. I want people char 1 and people char 2. And there you go. That's the one-hot encoding of that. So I could come back up here. And this is sort of the advantage of Jupyter, that I could be playing with this and just let's try people char 4, see what that looks like. And I get a different one-hot encoding. Now what I might do, I'm seeing that this is working, and this is this method right here that works to pull 2 columns and one-hot encode them. So what I might do is come up here and do def one-hot encode 2 calls, and then call 1, call 2. How's that look? I'm sort of coding blind here. And then bump it over. And then instead of printing, how about if we return this? OK, so now we've got a method defined.
You don't use call 1 or call 2 anywhere yet. I think you probably need to change attribute 1.
Thank you. How about if we do this? OK, thank you. So there's that method. And let's just pass them directly in here. And there it goes. Let's try it again. Let's try it with 6 and 7. There goes that. So at this point, I've worked on this method. I've abstracted it. I've worked on a script. I've abstracted it into a method that I've tested a little bit. I see that it works. So I might take this method and go pop it into a file in my library, and then go ahead and run something. I might put it into, say, for example, database helper, and then go from lib.database, or I think it was lib.helpers, database helper, import one-hot encode 2 calls. Oh, it wants to actually pull the methods that I actually wrote. I'm not going to put this into the file. I'm showing you this is actually what I did to create one-hot and outcome, one-hot encode row, one-hot from table, and one-hot indices. All methods that I used throughout working on this project that I wrote exactly like that. Are there any questions about that?
Very basic question.
Yeah.
What is one-hot encoding?
So one-hot encoding is taking each characteristic. So for example, if you had one column that had 3 characteristics, rather than calling it, making them numbers like 1, 2, 3, you have a binary on column 1 or on attribute 1, a binary on attribute 2, and a binary on attribute 3. So you turn a single a single attribute that's a characteristic into 3 attributes, each one being a Boolean on whether or not it is that. Yes. Or it's A, not B, not C. Yeah. And I think, nope, there's that. So the next thing to do after that was to write the one hot to the action table. So I actually wrote these methods, pull actions and one hot in code. A limit of 1,000. I really wanted to do 1,000 at a time. And then this is going to give some action IDs. For these action IDs, run pull actions. So pull those actions and then one hot encode the rows. Let's actually look at that, because this one, as you can imagine, takes a little while. There it is. So I've imported Q. So I'm going to take this job, and this is actually how you pass an argument to the Q, or pass a function with arguments to the Q. You don't wrap the function in parentheses like you normally do. You just add the arguments to the end. And this is built into to our Q. Let's kick this off, and then I think we're going to have to wrap up. So it's going. Let's see how many we have. 840 so far. Let's go take a look at our worker. We only have one worker going, so it's not going very fast. Last thing. Let's add some more workers. What's that? Okay, I know what that is. So we're going to do workers equals 8 make workers. And Docker Compose just scaled it up for us. And if we come back here, now we have 8 workers. Cool. So we're going to have to wrap up. There is a lot more that will be in the presentation online at the GitHub address, and I'm sure they'll make it available as well. Are there any questions from what you saw so far, or any questions at all?
Basically, you're going to spin up a whole bunch of DigitalOcean images and then
That's the idea. That's actually what Swarm is. So with Swarm, you take multiple DigitalOcean nodes, and you swarm them into and they behave as a single Docker machine. And so what it does when you request a new container from the Swarm, or you tell the Swarm, I want to instantiate a new container, a new process, the Swarm says, hey, who's available of the nodes? And the one who's the most available, or if there's a tie, just randomly chooses one, gets that container. And so this is a way to scale up. Yeah. But what's great is when I'm running this on my Mac, it's a quick and easy way to get access to all 8 cores. Yes?
Is there a particular reason why you chose DigitalOcean rather than AWS?
Yeah. I can talk about it outside afterward. I mean, it's I guess it's sort of like an underdog kind of thing.
That's not like a typical.
No, I mean I've used AWS, and I think that like I use AWS. It's just I don't know. I like DigitalOcean, and you know what it is. When I started learning all this stuff, I would go look for go Google how to do something, and there was always a DigitalOcean tutorial saying this is how you do it, and what's that?
And those work.
And then they work, and so I sort of have this this affinity for them. They sort of taught me how to do this networked computing hacking. Yes.
Can you show your link, your GitHub?
Yes, absolutely. Thank you.
The presentation titles are different, but similar.
Yeah, I added Jupyter in. It was like when I was making the presentation, I realized that it was all about Jupyter. What's that?
You have scalable computing for individuals.
Oh, it says scalable. High performance, scalable. Tomato, tomato. Cool, thanks.